Hello, everybody. Good afternoon. Okay, welcome back. And today we're gonna finish the recurrent neural network parts. Okay, what we haven't covered is the gated recurrent neural networks. So we will start from the so-called gated recurrent units, which is GRU, and then Lstm, long short-term memory. So the ideas of these two architectures are pretty much similar, and they are all designed to address the long-term dependency issue that is not the advantage of simple recurrent neural network. Like simple recurrent neural networks can model languages, but it's not easy to capture the relationships or dependencies between words that are farther apart. That are, for example, how to predict my next words based on the sentence that I said more words ago or more sentence ago. So it's like the difficulties in modeling human language that drives the design of these such gated units. Okay, so we will look at these two architectures first, and then there will be some extension based on the simple architectures. We will introduce the bi-directional structure and the deep architecture as well. So, and I think we will have some time left for a Jupyter Notebook demo for how to use recurrent neural network in PyTorch. Yeah. So, all right, and let's get started with the recurrent unit first. Okay. So, so what is the long-term dependency issue? So let's go through some examples. So these examples, for example, the first sentence, the cat followed by a which clause, like which already ate, blah, 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 right? And the verb for the cat was, right? So the verb was refers to the subject, the cat, okay? So ideally, we want the language model to generate was in this case, right? And for the second example, if we're using the model to take this previous context as inputs, it reads the cats, now it's the plural form, right? Also followed by a clause, and then a good model should generate a different verb, like were corresponds to the cats, right? They're different morpheme, right? So how does the model memorize the plural form versus the singular form of the subject word is a difficulty actually. So because basic RNNs does not capture the long-term dependencies. Because of if we are using simple RNN to model these long sentence, then because of the nature of the back propagation through time, because we set a truncated window for that back propagation, the information at an earlier stage is very hard to pass along to the this position where the information, whether the subject is cat or cats, is actually very little information is kept, right? So we need to figure out how to deal with this issue. Yeah, and the second example also showcase a similar problem. Gandalf was one of the most powerful wizards, who, right? So whether we should use the correct form of the proper nouns. Actually requires the model to memorize the information that is a very long distance ago, right? So we need to have some mechanism designed that deals with the vanishing ingredients issue, so that even if it's several words away, several words ago, that information can still be kept within the model, okay? And that's why we designed the gated recurrence unit, yes. So here's a slide shows that just a review of the gradients vanishing issue, because in the back propagation through time for RNs, we know that the gradients for parameters at different time steps, right? They can get smaller and smaller, right? Because the terms that we need to multiply along with the gradients gets longer and longer, right? So these DUs, for example, at the first time step is actually a product of such a long multiplication expression, which could be very close to zero, very small values because of the vanishing gradients issue, right? All right, so, and the gradients, the magnitudes of the gradients basically characterize the degree to which that the parameter plays a role in determining the output, right? So the smaller gradients means that the information at that time step is playing, if that gradient is small, then it means that that time step is not playing a very important role, right? All right, so we need to figure out a way to deal with the vanishing gradient issue, basically by preserving part of the gradients through a different channel, rather than keep everything within this one channel, within the activation, within the hidden state activation. Okay, right. Sometimes the activation can also be too big, right? So this is another issue, but we also need to deal with that. Okay, so primarily speaking, we want to deal with the vanishing gradients issue in training an RN model. Okay, because that is critical for us to capture the long-term dependency, right? So we will use a simplified way to visualize the basic RN. Okay, so within this graph, it's still basic RNs, right? We will first plot the internal structure of the model like this. For example, we are using the 10H as the activation layer for the internal activation function. We take the inputs xt at the current time step, right? And the activation from the previous time step, which is a t-1. And they will concatenate it and be fed into a linear model, model followed by a activation function, right? And that's basically how we compute the activation for the current time step. And then this activation will be used to compute the outputs of this current time step. So this simplified computation graph shows how the data flows within the current time step, right? Xt flows to the 10H function, right? The activation of the previous time step flows this way, and altogether they compute the AT together. And AT is also used to compute the outputs of this time step, for example. So we're gonna do some modification to such a basic data structure, right? So the gated recurrent unit, GRU, was first proposed in 2014, right? And it was first proposed to be used in general sequence modeling, and also in a encoder-decoder based machine translation task. Okay, so the key technique is that it uses something called memory cell. Okay, this C of T is the memory cell, which is in addition to the activation A of T. Okay, so this memory cell is used to keep long-term information or long-term memory, such as whether the subject of the sentence is a singular form or plural form, right? So in GRU, the memory cell is the same one as the activation cell, okay? And at each time step, we will consider overriding this memory cell with some candidates C tilde, okay? So it's not a direct overriding, but we will, before we overwrite C of T, we will first consider some candidate C tilde, and the C tilde is computed with the previous memory cell and the current A of input. So far, this step is not different from the basic RN, right? We just changed the letter from A to C, right? Everything else is basically the same, except for the subscript, right? So this is the C tilde, right? So we don't directly override C tilde. We come up with some candidates, okay? And these candidates is something that we will use in combination with some gates, okay? This gate is important here. The gate is called gamma U, and it's an gate that has the value between 0 and 1, okay? And this gate controls how much proportion of the candidate we will use, okay? So for example, in this case, we will use the previous memory cell contents together with the current inputs. And this time we use a different weight matrix called the weight matrix for the update gates, right? And this gate is from an sigmoid output. So the values for each elements in this gamma gates is between 0 and 1, right? And the U is for updates. Okay, so this basically this gamma determines how much we want to update the contents. Okay, so now when we update the content cell, the memory cell C of T, we will use the gates. Okay, it's basically the weighted average of the candidate C tilde and the previous memory cell, right? So it's gamma U times the candidates plus Y minus gamma U times the previous value. So this weight produced by the gamma is actually creates a balance between the new candidates and the previous value. Okay, so as you can see that there's some additional step, like this internal gate is the additional step compared to the simple RN, right? Because in the simple RN, we will directly compute a new value through this 10H, and we will override C of T directly, right? If that's the traditional, if that's the simple RN, right? But this time we insert this gate and as a way to for a second thought, right? Before we actually update C of T, we need to consider the candidates. We will first construct some candidates, right? We are more conservative in update the C of T, right? We let the gate to decide how much does it think whether the new candidate is more informative or the previous memory cell content is more informative, right? So because the outputs, the gate is from a sigmoid function output. So the property of sigmoid is generates some value between 0 and 1. And another property is that it's actually easy, can saturate really easily. It's like the values of the update gate it's basically either 0 or 1, right? So it's a way to determine whether we will take the candidates or take the previous contents. Okay, If the memory cell is 1, if the memory gate, the update gate is 1, it means that we will use the candidate C tilde to update the memory cell. Otherwise, when the gate is 0, then it means we don't update the memory cell, but we will use the old memory. Okay. So and this gate is in the same dimension of the memory cell. Okay, it's actually a vector itself. Okay, so actually having this gate mechanism designed actually have a very good result in sequence modeling task and in machine translation task as well. Okay, so how we interpreted this, how we explain why this works, is basically to say that our gates set at this place serves as a way to select, right? It gives us an option to be more bold or be more conservative, right? So you can think of it as an it's kind of similar to the residual network, and also it's similar to the mechanism of momentum in when we talk about optimization algorithms, right? So it's like a weighted average of the previous information and the current new updates, right? But it used some gates. It let the gate to decide whether we need to trust the new candidates or the previous information, right? So, for example, in this case, this is just for a demonstration, right? So we, for example, we assume that the memory cell equals 1, means that the subject is a singular form, right? And then at the next time step, the gates can probably be 0 because that singular subject information is still useful, right? So it will the gates will be always 0 until the point that after the was generated, right? Then the gate can actually be updated, because after the verb is used, the singular form information for that subject may not be as useful afterwards. Okay, so this is just a imaginary example showing how the gate can be useful in sequence modeling, in sequence predicting or sequence generation. Okay. All right, so let's look at the internal structure if we want to visualize the structure. It will be like this. Okay, so compared with the basic RN, the input end is basically the same, right? So we don't use activations anymore, but use the memory cell CLT, right? And the X inputs XLT, right? So the connections between those arrows means that we are combining different components. For example, the C tilde, let me use a different color. The C tilde here is the result of using previous contents and the current inputs, right? So these two will be used to compute the C tilde, right? And the gamma will be, the gates will be used also using the previous contents, right? But now it's a different pathway and the current inputs, right? So this resulted gates gamma and the previous and the C tilde will be used together to compute the current new value for memory cell, right? Okay, so in reality, the gate is very close to either 0 or 1, right? It's an empirical observation that it's rarely between, for example, it's rarely somewhere between 0.5. Okay, so what does it mean when the gate is 0? So it basically, when the gate is 0, right, there's actually these components would be 0, right, and these components will be almost 1, right? So if that is the case, then these pathway doesn't take any effect, right? So it's actually only the C of t is taking effect, right? C of t is determining the current time output, the current output of this current time step. So it means that we are purely using the previous information, right? When the gate is 0, update gate is 0, right? So, and when update gate is 1 in the opposites, we are cutting this connection from the previous information, but we're using the current time step to do the prediction for the current time step, right? So it gives a very flexible capability for the model to decide whether we need to trust the current time gates, the current inputs or the previous inputs. Okay, so it's really useful in to mitigate the vanishing gradients issue. Okay, and actually, what we have just proposed here is a simplified version for the GRU units. Okay, and if we look at the, if we read the paper, and if we follow the Rn, this pretty famous Rn posts, it will be like, actually, we will need to construct not just the update gate, right, but also some gate called relevant gates. Okay, and these relevant gates, how we construct it is also to use the the previous memory cell and the current inputs, right? And the resulting relevant score will be used to compute the candidates of the C tilde, right? So it gives more. Flexibility in describing how important, how relevant the previous content is in deciding the current candidates, right? So it basically makes the model more flexible, right? And this whole structure has been proved to be more effective in modeling not just language data, but also in general sequence predicting, right? Could be any time series data when the memory cell is used. The predictability, like how accurate the future events can be described, is much better as compared to the non-gate units. Okay, so that's GRU, and the second example that we're going to cover is more famous. It's called long short-term memory, or LSTM. Okay, so Lstm proposes a very significant modification to the Rn-based simple Rn, because the previous GRU is still similar to Rn because there's only one information pathway from the previous time step to the current time step. Okay, but what Lstm proposes is to separate these two types of information passed between time steps. It separates the memory cell and the activation. Okay, and it's basically treats the memory cell as the long-term memory, and the activation as the short-term memory. Okay, so it's basically separate set up two types of memory, two types of historical information. Okay. So in computing the candidates for the memory cell, it uses the activation of the previous time step. Okay, not the contents, not the C from the previous time step, together with the current time inputs. Okay, so that is the candidate for the memory cell. And the update gate is similar to what GRU has, right? It has updates that uses the current, the previous activation and the current inputs. So this gamma U is the gate for updates. Okay, and it has something called forget gates. Okay, so that is different from the GRU. Okay, so it uses the forget gate, which is also computed from the previous activation and the current time current inputs. All right, now we have two gates, right? Update and forget, and it will also have an output gate. Okay, just more gates, right? So we have the activation from the previous time step and the current time step. So this gamma O, as the name indicates, is in charge for deciding the weight we put in computing the current output. Okay, so we have three gates altogether, right? Update, forget, and output. Okay, so the new value for the memory cell will be the weighted summation of the candidates and the previous memory cell. But this time, the coefficient here is not 1 minus gamma U as GRU used, but this time we used the forget gates, right? You see, the update gate is multiplied with the candidates, and the forget gate is used to multiply with the previous memory cell, right? Because the gate controls how much we want to forget about the past memory cell, right? So that's basically how this memory cell is computed. And the activation, the new activation is used as the 10H of the current memory cell, of the new memory cell, together with the output gates. Right? This is an interesting interrelationship, right? So the C that we computed will be used to decide the activation of the current time step. And at the same time, the C is also determined by the previous A's, right? The previous A's is here, the previous A is here, right? So these A and C, like they intertwined, right? The long-term memory will partially decide the current short-term memory, and the short-term memory will also decide how much long-term memory we want to preserve. Okay. Okay. So that's a very salient characteristics for LSTM. We have three gates, right? So compared with GRU, well, in GRU we only have in the full version of GRU we only have update gates and the relevant gates, right? So if we look at the structure, a significant difference is that we can see two pathways, right? Two horizontal paths between time steps, right? So not just the memory cell carries some information, but also the short-term memory also carries some information between time steps. And it looks like the memory cell is carrying over, it's more easy for the memory cell C to carry long-term memory, because there is a straight line. It's almost a straight line, right? So if the gates controls the update gates is 0 and the forget gate is 1, then basically everything in the C will be carried on to the current time step, right? And the activation actually can the second information pathway, the activation actually can be changed pretty often, because finally it will be changed. It will be determined by the output gates. Okay, and the output gates will be used together with the previous memory cell. Okay, so that's two pathway in the long-term in a LSTM computational graph. Right. So that's the most significant difference between the GRU. There are two variables, the C and the A, and they basically serve as two functions. Okay. So the long shorten is determined from the paper that's actually published in 1997, right? So if you are interested, this is a classical paper to read. But back at that time in 1996-7, there's no such a concept of deep learning, no such a concept of very well defined tools to help us to engineer everything very quickly. But it's purely a mathematical concept at that time, and I think it's a really impressive achievements of coming up with such an idea that influences the model designs 20 years later. Okay, so typically people would believe that the memory cell carries long-term memory while the activation carries short-term memory. So if we use LSTM to model a sequence of sentences or a sequence of words, for example, usually speaking, we would believe that the memory cell contains information that determines, for example, whether a word should be plural form or singular form, right? So I believe there are computational linguistics studies about this to check how the different memory cells can be predictive about the different grammar components. Okay. All right. So one thing about Rn is that once the internal structure has been captured, has been designed, then we can think of it as a standalone model, as a single component, and we can just ignore the internal details and treat it as just as a recurrent unit. So, for example, we have LSTM defined, and then we can put it into a box, and the function of that whole one box, right, one green box, is to take the inputs at a current time step and some previous information to compute the hidden states of the current time step. Right, this hidden state can be used to feed into a softmax, right? A softmax to predict some outputs, right? So these is basically the same units, the same structure, right? Repeatedly used for different time steps. And we can do this for the basic Rn. As you can see, that the difference is that all the architecture looks pretty similar. It's like we use inputs for each time step. We not just use the current inputs, but also the previous inputs, right? And for LSTM, we use the two channels, two information paths, which is the long-term memory and the short-term memory. So that is something we should keep in mind. All right. And as a simpler graph notation, we don't need to, when we try to tell people that we're using LSTMs, we don't need to like draw the internal implementation details, the internal structures. We just use the LSTM thing to indicate that it's an LSTM block that we use. Okay. All right, that's pretty much for GRU and LSTM. Any questions so far? Right, so If no questions, we will talk about the next part, which is the bidirectional Rn, right? So it's a and very natural extension on the simple Rn network, right? For example, let's use the same example again. We use this example to show that it's important to use the future words, to use the words on the right of Teddy, right? The next word basically determines whether Teddy should be a person's name or a toy's name, right? So that means if we use a simple one-directional Rn, the first two words he said would not be that useful in determining whether Teddy should be a entity, a named entity or not, right? So altogether, we need to think about the problem from a different direction. Like if we are modeling the task, modeling the sequence from right to the left, then we are able to use the information from the word Roosevelt, right? Roosevelt to predict the word Teddy. So what we can do is that we first set one layer of neural network like this, one layer of Rn like this. We have A1 to A2, A3, A4. And this A, if you look at closely, we have a left to right arrow, right? Indicates that this is the one direction activation. And for the next, that's called a forward direction. So note that this is not the so-called forward pass in a competition graph. It's just a way to indicate this is the left to right direction. And the backward direction actually starts from the fourth word, the last word in this case, right? And the activations used in this case has a right to left arrow. Okay, so it means these two representations, they are different. Okay, they are different. And then we use A4 as the first inputs, right? And then it's fed to the third word, which is Teddy, right? And to the second word and the first word. And altogether, these, both the forward direction and the backward direction, their representations can be concatenated or be weighted, or be fused together with some mechanism so that to predict the outputs for the current time step, for each time step actually, okay? So the y hat of t would be the results of utilizing both activations from the forward direction and activation from the backward direction. Okay, so this is a kind of the nowadays the default option for, well, not default, but it's a very commonly used technique to modeling sequences. Okay, not just in language, but also in very generic sequence modeling tasks. All right, so let's look at the second type of more advanced architecture, which is called multi-layer Rn. Okay, so it's the idea is drawn from the deep neural networks, right? So in very, like, let's go back to the regular network. So after we have introduced the shallow neural network, we started talking about the deep network, right? So we just stack multiple layers of parameters so that the output from the previous layer can be used as the inputs for the current layer, right? So that's multiple layers is not across time steps, but within the same time step. But we can do the same thing for RNNs, right? It's like we can use the activations from one layer of RNN, right? The outputs here, if it just, if it's just one layer, then these will be directly the y hats, right? But we can keep using this information. We can keep using this information as the inputs for another layer of neural network, right? Which we can call A with superscript 2 in square brackets indicates that this is okay, our second layer of network. And we can put even higher layers, right? And after 3 layers of network, then we will eventually get some outputs. And all the purpose of these multiple layers is to have more parameters to come up with more more informative representations of for each time step. And I think that is the same thought as why we use multiple layers in regular neural network. Okay, so for example, in this particular case, the activations for a superscript 2 within the brackets and the 3 within at the third time step is actually when we compute this activation, the left parts with A22 and this bottom part A12 are used together. Okay, so this is a very typical visualized way to think of the problem. Like the activation at that of this time step at this layer is the result of using the intermediate outputs from the bottom layer and the previous time step. Okay. All right. So it looks very complicated, but nowadays actually in PyTorch we can easily set the number of layers to tell the model that how many layers I want. Okay, and we just need to get familiar with the grammar that's okay, how to call the function correctly. Okay, that's for multiple layers. So in practically that 3 layers is already very deep for, and we don't necessarily go any deeper. Okay, and of course we can combine the two, right? We have bi-directional layer. We have bi-directional Rn for each layer, and then we can stack multiple layers for LSTMs, and we can add fancy connections like skip connections, like the way we did for ResNet, right? Yeah, but as this picture shows, this is used for speech recognition tasks, right? But nowadays, I think the state of art should be transformer-based models. But transformers models is not a recurrence-based mechanism, but it's based on self-attention and the feed-forward, yeah, which I think we can cover a little bit in the future. Right. So, okay, it's time to look at some PyTorch examples, right? So let's finish the slides in these with some code examples from the PyTorch websites, and then I'm gonna go through a tutorial, not a tutorial, but several examples in a Jupyter notebook. Okay, so in this example, for example, the task is to classify name types with character level Rn. All right, so basically, it's a character level recurrent neural network, right? You know, we are not treating one word as an input, but one character, right? So the inputs for the first, so the input, not the output, the input name Hinton, right, will be converted into letters with H, I, N, and so on, right? So that is the character level Rn. And the way that's the code is designed, if we design the model manually with basic Rn, it's basically we need to design several weight matrices, like this input to output. This is a weight matrix, and this I to H is also a weight matrix, also probably with bias terms. And the hidden layer at the current time step will be feedback to the next time step. Okay, so that is how the computation graph of how we want to do this manually. Okay, but actually we don't need to do this from scratch actually. So we will have let's look at the code if we want to design this from scratch, right? So we can call
we can design some class as the subclass of the end-of module, right? And within the definition, right, we have these I2H and the I2O, which are weight matrix defined by this end-of linear, right? This is how we define the very deep neural networks previously, right? And the softmax is also the default softmax in NN, right? So the tricky part is the forward parts, right? So because the recurrent neural network, at each time step, it will take the xt as inputs and the previous activation a of t minus 1 to generate some new outputs and a new activation, right? So that is a simple activation layer. There's a simple neural network. So in this case, we need to take the xt and the at minus 1 as input. So you see, look at the forward function. There are two parts. It's the inputs that corresponds to the x, and the hidden actually corresponds to the a, right? And within the model, it will first concatenate these two parts, right? And then feed it into some and use the combined inputs to compute the hidden representation, right? And then to compute the outputs, right? This case, just for simplification, they don't use, this example doesn't use a nonlinear activation, right? So this is how hidden and outputs are created. And then the output is fed into a softmax. And the important thing is that the hidden and outputs, the hidden is also returned. Okay, the hidden is also returned, so that the hidden returned from the current time step can be used in the next time step. Okay, so that is how the code is organized. So we can take the input from the current time step to predict all the future time steps. All right. So that's for the RN model. So, and in an example, the example from the PyTorch website is to convert the letters in the J to a one-hot encoding, right? So I'm gonna skip this quickly because we will have a complete example showing how the data are organized in PyTorch RN model. Okay, so the way that models are trained is pretty similar to the CNN models or the regular neural network models that we used before. Okay, so the data will be used to compute some outputs, and the outputs will then will be then compared with some category with some criteria function to compute the loss, and the loss will be used to generate to conduct the backward propagation, right? And the parameters can be updated. And if you don't want to do this manually, you can define an optimizer to do that for you. Okay, so that's pretty much for the recurrent neural network. So I think I will start talking about go through the Jupyter Notebook examples to showcase some PyTorch code here. You can see this, right? Okay.
Yeah, the top of our screen says import torch torch.nn as nn.
Yes, great. All right, so that's basically what we need to use here. And I'm going through two components, actually. So after we import this, right? Actually, I don't need to run it again. And what we're gonna look at is this, first is this RN cell. Okay, so we'll first talk about this Rn cell because it's a more basic unit, right? And what it does is to handle the computation for one time step. Okay. It doesn't compute the complete computation for all time steps automatically for you, but it gives you the flexibility to design how the activations between time steps can be modified, right? So this Rn1 that we designed is an instance of this Rn cell, and the input 20 means the size of the inputs. Okay, the first parameter. The second parameter 30 is the shape of the hidden states, right? So it basically means that the inputs at each time step is a vector of 20 elements, and the activation is a vector of 30 elements. Okay. All right. So how we construct the input sequence is to use torch.random normal a random number from a normal distribution to create a tensor that is 5 by 12 by 20. Okay, so the meanings of these dimensions actually matters, and the defaults for PyTorch is that the first dimension here is for time steps. Okay, and the second is for batch. That is the default meaning for meaningful input to the Rn cell. And the last dimension is the input side. So we have to make sure that the last dimension is 20, right? And all these previous two numbers can be actually, you can change it yourself. Like you can make sure that your input, you can change your input to contain like more than 5 time steps. You can have multiple time steps, 6, 7, 8, or whatever number you want. And the batch size is also something you can change. It basically tells that how much sequences do you have in one mini batch. Okay, so in this case, we have 12 sequences, and each sequence is contains 5 time steps, right? And within each time step, it is a vector of 20 numbers. Okay, so one implicit assumption is that all of these 12 sequences, they are of the same length. All right, so that is not sometimes it is not a flexible enough, right? Because if we want to say put 10 sentences within one mini batch, then it is very likely that the 10 sentences are of different lengths. The first sentence may only have 3 words. The next one can have 12 words, right? So how about we deal with this variant length problem? Is that we can choose to pad those missing elements for those short sequences, right? We can append some zeros or ones or special tokens to indicate that this is a padded data, right? But PyTorch have a more complex mechanism to automatically to not automatically, but to pack data for you, and then also unpack the data after the input has been fed into the Rn. But that is out of scope for this demo. So let's look at the nature of how the data run into the Rn model, right? All right, so here the inputs, I showed the shape of the first sequence, all right? So because the second dimension means the batch, so if I access the first elements, if I give a 0 to access the first elements, that's, and also 2 columns here, that will give me the first sequence. Okay, so the shape of it would be 5 by 20, which means we have 5 time steps, and each time step is a 20 elements. Okay, and if we rerun this again, right? So actually, let's comment this out. We'll see that the sequence of these, the shape of these two sequences are the same, right? Right. That's why we can put them into the same tensor. Okay. All right. Now let's look at how the code is for running through a single sequence, with this Rn model. Okay. So we need to define some hidden states activation, right? Because the Rn cell is defined as 20, 30, which means 30 is the hidden states, the size of the hidden state. So the hidden representation that we define should be in this shape. We give it additional batch size, additional dimension, right? So because this is the default option for PyTorch, if I remove this one, there will be a error in the program. So the PyTorch assumes that you need to give it a dimension for the batch, even if there's only one data instance in your batch, right? So that is the case for this single sequence. So we'll put a 1 here, right? And the way that we run through this example is that we will use a for loop, okay? And the purpose of this for loop is to go through each time step, right? So the 5 here actually corresponds to the 5 here, right? Because our inputs, we tell the data indicates our input has 5 time steps. So the for loop should also be that 5 time steps. And in each time step, the Rn cell, right, will take 2 inputs. The first input is the current time step within the sequence, right? So that's sequence 0, right? We use sequence 0, which is our first sequence, right? The sequence 0 of I indicates this is the i's time step for sequence 0, and we use a unsqueeze 0 with the same reason as this additional 1 dimension, because we want to make it a batch size 1, right? So that's just a trick with PyTorch. And the second input is h, which is the time step from the previous, which is the hidden activation from the previous time step, right? So initially h will be 0, right? But after that, the h will be overwritten, right? We will, after the new activations, new hidden states is computed, we will overwrite the values for h, right? And the output 1 will, the new activation will also be appended to output 1, right? So after we run this, if we print the outputs or print the size of output, we actually can find 5 elements in it. And each element is the activation for that time step, right? Each one is a torch that is in shape 1 by 30. Okay, so that is how we handle the inputs using the Rn cell as an example. Okay, but that is the first example running through one single sequence. Okay, and the strengths, actually the advantage of using PyTorch is that you can handle data in a mini batch, right? So we can actually run through the Rn cell with multiple sequences, right? Remember, our complete sequence data is like 1 by 12 by 20. It's actually 12 sequences, right? So now, if we want to run through this cell with 12 sequences at the same time, then we need to define the we need to initialize the hidden states in such a shape in 12 by 30. It's no longer 1 by 30 because it's 12 sequences, right? And in this case, we use output 2 to store the results, and we will need to use a same for loop to go through each time step, right? And the H will be overwritten, right? But this case, the inputs is different. The inputs is the input sequences, the I's input sequences. Remember, the input sequences in this shape, right? So the first input sequences would be a 12 by 20, okay? So this is just another way to accessing the first time step. We are actually accessing the first time step for 12 sequences at the same time, right? Not just for one sequence, okay? So the results is the activation, the H is also for 12 sequences, okay? So if we plot, if we append H to the output 2, and if we look at the length of output 2, it's still 5, right? And each one is for one time step, but the shape of one element in 12 in output 2 would be 12 by 30 because that's for 12 sequences, okay? And I also compared how close the output 1 from the previous time step, because output 1 is purely from the first sequence, right? So theoretically, if I look at output 2 of 0 and 0, it will give us the time step. Actually, the activations of the first sequence at the first time step, right? They actually should be the same thing, but it turns out that there's slightly difference. There's one position, one dimension, there's a little miss, right? And I looked at the difference, it's very small. So looks like the results, the numerical computing still depends on how you organize the batch, right? When you organize 12 sequences, somehow the underlying mechanism, numerical computing would be different. All right, so that's for Rn cell. And actually, the third example that I'm gonna show is a more powerful one, because the Rn cells still have very significant disadvantage, because we need to use a for loop to go through each time step, right? And actually, this is not flexible, right? Well, a for loop in Python is not a very performance operation. And actually, if we use some more advanced techniques, it can allow us to avoid this for loop drawback. For example, the third example that I use is the Rn, right? So this is no longer Rn cell, but Rn. And Rn can take multiple arguments. Like I set 20 and 30 as the input, which is to be consistent with Rn cell. And the number of layers, actually, I set it to be 1 because the default is 2, okay? The default is 1, but I explicitly states that because I don't want to multiple layers, okay? And the bi-directional is also something we can try, but in this case, I set it as false, okay? So this Rn cell, what it can do is to take multiple inputs, the input at multiple time steps, and it will compute the between time steps computation directly for you. You don't need to use the for loop, right? So this time, we can directly feed everything in input sequence directly to the Rn2. You see, we don't use the for loop, right? We don't need to initialize a hidden layer a hidden activation manually. We just use this Rn2 to take into everything in the sequence, in input sequence to compute the results. Okay, so if we look at the outputs, right, the outputs here actually have 2 parts, right? The output has 2 parts. The first one is in this shape. Okay, it's actually at the same length as the inputs, right? It's the sequence. It's the same sequence length, right? And the activation, the dimension of it is number of directions times the hidden size, because in our case, number of directions is 1, right? So it's actually just the hidden size, right? And the second outputs, h of n, is actually the hidden states of the last time step. So here, number of layers is 1, and number of directions is also 1. So it's actually 1. Okay, so it's actually 1 in this case, and this is also 1 in this case. So it's actually 1 by batch by hidden size, right? So it's just the last time step, right? So if you look at the shape of out and the hn, it's actually the outs is 5 by 12 by 30. You know, we converted everything in the inputs from 20 dimensions to 30 dimensions, right? But everything else is the same. And the last dimension is the last activation is returned in hn, right? It's 1 here. It's just the last one within these 5 elements, right? But it's in the shape of 12 by 30, right? And if we check whether the outputs of the previous task, right? We checked whether the output 2, the 0 of output 2 is equal to the 0 of out here, right? Actually, they are the same value here, which means we run the Rn with 1 command, but it does everything for us that needs to be computed within this with this for loop in the second way, right? And the internal implementations for Rn is optimized at a lower level, so it's more efficient than the explicit for loop. So I hope this demo is helpful for you to understand how the sequential data are modeled in PyTorch in a modern framework, and also hope it's helpful for your homework for the Rn. And I'm gonna release the homework later this evening, and there will also be a quiz question about gated units. Yeah, one simple question about that. All right, I think, yeah, it's fun to play with. If you are interested in time series prediction, RNNs are really powerful tools to directly grab the code and grab some data to see how future can be predicted, and the PyTorch really allows for a really convenient way to play around with sequence data, and tons of details to explore though. So yeah, enjoy this running code. Yeah. All right, let me stop recording.